You doing? There. This should be a really quick chapter. I don't think there's really a whole lot that we have to go through here, other than there's a lot of different types of altitudes and speeds and stuff like that. We'll talk about that. Donnie, how you doing? Good. See if we can get two of them knocked out today. Two chapters. It depends on the girl that was supposed to come out from Sierra Space. I haven't heard back from her yet, but she's supposed to come up today. So we'll see if she. Are you guys familiar with Sierra Space? No? They make the Dream Chaser space plane. You're familiar with them? Um, yeah, she's one of their engineers there. They also make those habitats, which are really cool. They did you by chance? Yeah, did you see that? Yeah, that was fast. Yeah. They blew it up. Basically, they fill it up with air and then they over pressurized it to see what the maximum capability. I think it was like 147 psi. Yeah. They were so it's very strong. So they'll probably, I imagine they'll get the contract to be on Mars and probably the moon as well. They're incredibly durable. I don't know. Do they make them out of Kevlar or something? Yeah, it's like Kevlar strips. Is it? Oops. Oh yeah, that thing is a there. Let me yeah, I think what came in it was I think do you guys have like a spring break right now? Yeah. You do? Okay, yeah. So we're probably gonna be missing some students and all right. Morning. Trey, how you doing? Good. Just got back from Kansas. Did you? Yeah. Got home last night. Late last night? Not too late actually. You know, we may be able to get in the waiting list today. Guys. All right, I think we're just going to get started, guys, and play yourself. All right, so we're on chapter 8 this week. And we're talking about instruments. So there's I think most of you guys is almost going to be a review, I think, for everybody. We kind of talked about this in the past. So there's what we call the flight instruments in the aircraft. These are the instruments that tell us how the aircraft is essentially, roughly where the altitude that it's at, the attitude that it's in. So you've got obviously if you're flying along like this, the altimeter is going to look very similar to what we see here, straight level. So if we go back here, this right here would indicate a turn like this. That's the attitude indicator we'd see on the panel there like that. So this is called an AI or attitude indicator, artificial horizon. We just usually refer to it as an AI, artificial indicator, artificial horizon, HSI. And the reason why we have to have that in most cases is because if we go up in the air and you fly into a cloud, you're not going to see the horizon. Or if it gets really hazy in summer months, we get conditions where the visibility drops down to maybe like a mile, maybe a mile and a half or something like that. That's really restricted. If you're up at 1,000 feet, and you look down, it's a little foggy, and then you look straight ahead, you're going to see nothing but white. So that's why we have attitude indicators in aircraft. So this is again, these are all what we call flight instruments. You've got the airspeed indicator, or what's called an ASI, airspeed indicator, HSI, artificial horizon. And then you've got your altimeter. This obviously shows your altitude. This is the turn coordinator, and it's actually two instruments in one. You've got this right here, the aircraft. It shows you. It looks like it's showing you back, but it's not showing you back. It's showing your rate of turn. It's different than the attitude indicator. This plane doesn't move up or down like the attitude indicator. It just is locked right in there. What it's showing you is how fast you're turning, what your rate of turn is. It's an important point to remember because that's something, again, you'll see on the test. And I'll show you we'll kind of go through how to use that. This is well, it looks like a compass, right? But it's actually called, does anybody know what that's called? What's that? Heading indicator, yep. Or directional gyro, DG. It's different than a compass. A compass, this is a magnetic compass right here. And you see that the inside there, it's just kind of flopping around and stuff like that. It's very difficult to read your heading off a compass, because if the plane is shaking like that, or you move it around, that little indicator in there is moving all over the place, and it's not extremely accurate unless you're flying completely straight and level and not accelerating. That's the only time these things are going to be reading accurate. But in bumpy conditions, this is moving over. So we have to have another instrument in the aircraft to tell us, reliably what our heading is, and that's the directional gyro. And then we've got our vertical speed indicator. This tells us how fast we're climbing or descending. So that 5 there represents 500 feet. This represents 1,000 feet. That's 1,500 feet. That's 2,000 feet right there. So that's typical what you're going to see on a vertical speed indicator. Sometimes they refer to them, I don't see it that often, but I think they refer to them sometimes as vertical velocity indicators, but vertical speed makes more sense, VSI. And And they do use a lot of acronyms and VSIs for that, DG, and then your turn coordinator, TC. Altimeter is just referred to as an ALT, and then your artificial horizon and airspeed ASI. So these are collectively known as the flight instruments, as opposed to your engine instruments, which are going to be a different set. So this is the way a lot of pilots learn to fly, with these instruments right here. The new instruments are like this right here. They give you the same information and a lot more. So let's look at this and just see where all those instruments are. So this right here is what we call the airspeed tape right here. And this moves up and down. I'll show you here in a second on the sim. You'll see that. This is our altimeter right here. And you can see this person right now, this pilot's climbing up through, or right at 1180 feet. And then this right here is a vertical speed indicator. There's 100, 200, or 2000, right? I'm sorry. So you've got your marker right here. If this moves up here, we know it's 1,000 feet, 2,000 feet climb. And down here, this would be minus 1,000 feet, minus 2,000 feet. Here's our directional gyro right here. Now, the one instrument so we've got the airspeed indicator, we've covered that. Let's take a look. There's our attitude, or artificial horizon attitude indicator. If we go here, that's this whole thing right here. You see our attitude right through there. This is the center. This will move up and down. I'll show you this again on the simulator so you can kind of see that. So that's our attitude indicator. One instrument that's harder for pilots to recognize is your turn coordinator, this right here. Let's go back to the more modern presenting this. Your turn coordinator is actually represented up here. So this right here is your turn. Sometimes they call them turn and slip indicators, or turn coordinators. That's another term for it. But this right here, this little thing slides back and forth to show you the quality of your turn. So let's go back here. Let's see. Yeah. Okay. So this is a turn coordinator right here, and you see that little thing on the bottom there, that little ball that's moving around there. That's just showing you basically where gravity is. So if I am doing a turn and I'm not coordinated, it's going to show something like this. And the ball is outside the two little lines. That's what we're seeing right there. That's an uncoordinated turn, and that's just because it's, like if I was flying really fast, that ball would swing out. Like if I took this, just whipping around at that angle, that ball would want to go to the lowest point on that tube, which is there, and that's showing us where our gravity is. But because I'm just holding it like this, it's going to go from one side to the other because there's no acceleration forces acting on it. So on a turn, we want that ball. Basically, in all phases of flight, we want that ball to be in the center up there, and that indicates that their center of gravity is below us, which is what we want. There are a couple times where that's not going to be the case. We can do like side slips and forward slips, which we get into a little bit later on. That's like, so let's say I want let's say I want to get the aircraft down on the ground really fast. A couple things you can do. Let's say I'm up here at 3,000 feet, the airport's right down there, and I need to get down. What I can do is I can put the aircraft into a forward slip and press on our rudder here, right rudder, and get the aircraft to fly down like that. What you're doing is you're creating a ton of drag. So instead of flying, normally when we fly through the air like just straight through the air like that. But if I want to present a lot of drag to the aircraft, what I'll do is I'll give it full right rudder or full left rudder, and basically force it to fly like this. That's just creating a massive amount of drag, and it gets the aircraft down really fast. So in situations like that, you're going to see something that's going to look crazy like that. It's going to be pushed all the way over. Generally speaking, when you're flying, pretty much all phases of your flight, you're going to want to make sure that ball is center. If you fly for a long period with it off like that, then you literally feel like something's off in the aircraft. So, and also the plane isn't going to perform as well, with that. So, all right. So that's turn coordinator, and that's think of this as a little ball There's also two little indicators that come out from here to show you your rate of turn. So what is rate of turn? Let's go here. Um, if you look here really closely, it says turn coordinator 2 minutes down here. What that means is actually let's go to the simulator and I'll show you. Let's go here. So again, here's all of our instruments: their airspeed, attitude, altimeter, vertical speed, turn coordinator, or I'm sorry, the DG, directional gyro, and then turn coordinator. So let's go up and do what's called a standard rate turn. So what that refers to, by the way, that 2 minute turn, that means if you turn, if basically these wings right here swing down to here at that mark right there, after 2 minutes of being in a turn like that, you will have done a 180-degree turn. Let me just make sure I think that's what that is. Or maybe a minute. I think it's a minute. So yeah, 2 minutes would be a 360 degrees. Let's verify that. Let's use that. So, right, so let's go back here on the pause. So I'm just going to go ahead and take off here. Test that out. Now watch these other instruments as I take off. So your airspeed indicator is pretty easy. You guys know that, how that works. When we get up into the white arc, I'm going to start rotating the aircraft, pull it back. The altimeter, we haven't talked much about how that works, but basically the small arm right here, it looks kind of like a clock, but it just has 10 digits instead of 12. That small one indicates thousands of feet. So if this is pointing at 1,000 right here, or 1, that's 1,000 feet. This is showing hundreds of feet right here. So I don't even have to use the small one, the small hand right here. I know just by glancing at this that we're close to 1,000 feet. And watch it as we climb. The small needle is going to turn a lot faster. So let's go through it here. Let's make sure it breaks off here. All right, so again, the instruments are looking, actually just look at your flight instruments and see what happens here. All right, here we go. Sorry. Okay, we can see our airspeed indicator coming up. Now watch our, do you see our vertical speed indicator? So let me just get into a standard line here. Right. So let's take a look at our vertical airspeed, our vertical speed indicator. See how it's going up? That means that right now we're at about 1,000, well, about 900 foot per minute climb there, and get it stabilized here. Eventually it'll kind of stabilize and it'll stay in a climb there. So right now it's showing about 500 feet per minute. And we're in a slight turn right here. There, you can see in the attitude indicator, it's showing that. Also notice on the attitude indicator, this little line right here, this is basically the wings of the aircraft. And notice how, let's pause something here. I can zoom into that. It's mimicking what's happening outside. So you've got your artificial horizon right here, and then this would be your aircraft. If you're looking directly behind the plane, this is kind of what you would see. Kind of like if I go to our circle view, let's go here, we go back. So that's kind of the attitude that we're seeing. If I switch back into the cockpit here, it's the same thing. We're basically looking at the same image, except this is a facsimile of that representation there. That's what the attitude indicator does. The turn coordinator, however, notice that that's not moving up and down. Again, all it's doing is it's just indicating to you your rate of turn. So let me just see. Let's get this. What I'm going to do is I'm going to get it in a standard, what's called a standard rate turn. So let's pause here. Okay. Slow down here. easier to do it to autopilot. So let's take a look at our turn coordinator. There it is right there. Just get this trimmed out so I don't fight it so much here. Notice our vertical speed indicator now is reading about 0. It does fluctuate a little bit, but we want it to get it, basically so that it's not climbing or descending. We want to stay at this altitude, which is about 1,500 feet. All right, so what I'm going to do is I'm going to go into a standard rate turn. I'm going to try to keep that ball in the center there. And let's see, does somebody got a watch here? I watch. Yep. Can you time me? I want to do basically a 2 or 1 minute. We want to just time me for 1 minute. And it should be 180 degrees of turn when we do 1 minute at a standard rate. So here we go. So I'm at heading up east. There's our directional gyro right there. There's also our compass. All right, so I'm going to go ahead and I'll tell you when to start here, Jonah. All right, so we're on a heading up east. All right, I'm going to start a standard rate turn. Okay, so notice right there. I'm going to just keep it right there. Notice how the wing is lined up. Let me just pause just for a second here. So notice how this wing right here is lined up with that. That's what we want to see there. Okay, so but I have to keep it in a standard rate turn. So it has to stay like that, roughly in this position. I'm going a little steep there. Let me know when you've got about a minute on your steep back here.
I had to reset it because we paused it, so it's not bad.
Okay, look, are you
We're at 20 right now.
20? Oops. What's that? You do have a let me try again here once here, so just so you can see it.
Want me to do a stopwatch?
I already got a stopwatch.
Okay, let's try it again here. I'm just going to do, we'll just do, we'll watch it and call out 15 seconds and 30 seconds. So, okay, so now we're on a heading of west. So if I do a standard rate turn to the south, or to east, 180 degree turn, at south, it should be about 15 seconds. Okay, now let me know when you guys are ready.
All right, I'm ready.
All right, here we go. All right, start now. Again, I don't want to go too steep. I want to go this right here. There we go. So the wings are lined up with that little lever on the little mark on the
First time it's going to take.
It should take about 15 seconds to get to south. Did you get 15 seconds there? Or?
Yeah, it was
I'm
15.
just at
Yeah,
20.
21.
Okay. What was that now? Where we at?
You had 21 in south.
Okay. 30 seconds. Okay. I'll just keep it going through here. I'm a little steep on this, I promise. Fast
At 46 at least.
here. Okay. I'm sorry, what's that? Minute to get to north.
Yeah.
Okay, we started on west, so yeah, about a minute so 2 minutes would equal essentially 360 degrees of turn. Okay, so and again, I was doing a poor job of maintaining that. And obviously, in a real aircraft, it's a lot easier. This joystick just is difficult to get it to hold. Usually, in an aircraft, once you get it configured for whatever constant flight, it's pretty easy to just maintain it. So, but that's a distinction between a turn coordinator and a attitude indicator. All right, and that's an important thing to understand because you'll have questions on it, and also, in flying, especially when you're working with ATC, they're going to expect you to do standard rate turns, and you don't have to constantly look at this. You'll feel kind of what a standard rate turn is. You'll glance at the instrument, and once you establish your bank, you'll just look outside. And what I'm looking for there, for students, for instance, so I'll do a standard rate turn. Let's roll right there is my standard rate turn. Notice, let's pause here a second. This right here there's a slice that I'm looking at right here. I want to keep that constant throughout the turn. So let's see if I can do this here. So this is what I would actually point out to the student. This is where you're looking, not down here. You're looking at that slice right there. You want to keep that angle the same. So I'm going to unpause it. So I want to keep it, keep that basically right like that. I just keep that same line on there. And you can do this in real life, and you can actually draw on the glare shield of the windshield of the aircraft. I don't think your instructor would let you do it, but if you could, you can actually draw this. And if, as long as kept the aircraft at that same view there, that attitude, I would stay in a constant rate turn there. A little steep there. So anyway, that's something that's, again, you'll probably use when you get out flying. Now, what some instructors will do, and I do this all the time, I'll take a piece of tape and just put it on the glare shield. I'll actually put a little mark, on the shield. I'll just say, okay, circle that, I'll put it around the shield. I'll say, make that mark, use that as a reference point. So it was here. So let's say I wanted to land, on a field or something like that. I would put that little dot where I want to land at. So, all right, I want to land where that dot is. I'll use it as kind of like a little aiming mark there. Yeah. And this is a technique that a lot of pilots will use for coming in for a landing. I did line it up quite right there, but you'll use that mark there to get down. And it's a good technique initially to help you understand how the plane, how it functions, what's happening to it. You can use just sometimes a scratch on the windshield itself. If you're coming into land, you'll use that as a reference as you come into land. So, all right, let's go back to our instruments. So now, how do these things work? So we've talked about all of them. Does everybody understand what these things do? These flight instruments. Okay. Vertical speed, again, pretty simple. Altimeter, you can see it working. You guys saw it go up. So this right here, can anybody tell me what altitude this is reading right here?
No.
Yep, 1,500. Yep. So you read this right here, it's in the thousands. The short indicator right there, it's pointing roughly. I mean, you can kind of see that it's about 1,400 feet, somewhere in there. But then this gives us the precision right here. It says you're at 1,425 feet, something like there, 30 feet, somewhere around there. And then so once you see how that works, it's not like a clock. In that sense, the way it works there. This small indicator right here, that really narrow one, that's in 10,000s. That shows 10,000. So you can see here, that would be, one would represent 10,000 for it, right here. And two would be 20,000. So it would be way up there. Obviously, generally, it's not that significant for a general aviation. Yes, that's above sea level. Well, we'll get into that because it really depends on how you have it set up. But yes, yeah, it would always be above sea level. So there are other factors in there. So we'll actually get into it in a second when we talk. There's a little window over here. If you look really carefully, there's all these little numbers right here. This is the current barometric, ambient barometric pressure that you should have in there. And notice if I change it, well, yeah, we pause right here. So I can just do this. Crash here. If I adjust this right here, it's going to see how it changes the altimeter. That's the what we call the Boltzmann window. We'll get into that in a second here. So, but yes, it would be mean sea level. Yes, yeah. It's actually it's pretty close to level right now, but you can see that little dot right there. It's actually just in the brown area. So that means if I look outside, we should be pointing down slightly. So let's zoom out here. Yeah, we're in a slight descent right there. But you can see how you could just use just the flight instruments to kind of figure out what the aircraft is doing, how fast it's going, the altitude it's at. Here we can see we're in a slight descent right here in direction. So all of that stuff can be used. Now, when you fly instruments, only you get your instrument rating. That you'll be looking at these instruments all the time because you're going to have a hood on. They will not let you look outside when you're doing your instrument training. Sometimes they put like little curtains or something like that over or it's not like a curtain, but it's a colored film they put on it, and they have you wear glasses and you can't see anything outside. It's just black. But for instrument training, you need to have that because if you're going to be flying in the clouds, you're not going to have reference to the outside world. And it's amazing. You think, okay, yeah, this is going to be easy. Your body, after a while, like half hour or so, or something like that, your body is telling you something different. It's saying, oh, I think you're in a turn, and this is what, you kind of feel, and it causes problems. So anyway, we'll talk about that. So let's actually now discuss what these different instruments are made of. Let's go back here. All right, so this right here, and we've seen it before, actually. Let's go back to our image here. I'll show you this on the outside. Okay, so over here, there is a device that's called a pitot tube. That's it right there. It's this thing right here. It sticks out from the aircraft there. You see that? It's just a little hollow tube, essentially, that's plumbed. It's got like a little pipe that goes into the cockpit, and it feeds the airspeed indicator. And this is essentially all it's doing is it's measuring the amount of air that's hitting the aircraft. And by doing that, you can determine what your airspeed is. So this is a typical airspeed indicator right here. It's just got a needle on it, and then it tells you how fast the aircraft is going. And again, it's not based on your ground speed; it's based on your airspeed. Obviously, if I were to blow into one of these holes here, I could actually get that needle to move. The other thing you could do is take a tube out here and run really fast. Let's say you hold it outside your car window or something like that. That needle is going to start moving based on the speed that you're traveling at. So if a plane is just sitting on the ground and you've got a strong wind, so let's say it's sitting here on the ground, and you've got a strong wind, 40-knot wind, that's the same as if you were flying at 1,000 feet and traveling at 40 knots. It's the exact same thing. So again, it's not measuring ground speed; it measures the speed through the air, and it's that impact pressure that's occurring there. Does that make sense? Okay, all right. That's the airspeed indicator. There's some other parts to it here. So let's go here. So this is what, and again, it's pronounced pitot. This is the name right here. You'll see it's not pitot or something like that. It's called pitot. It's a French term. So, but again, this is just a hollow tube that goes through there, and then this is again plumbed into the airspeed indicator. The airspeed indicator is the only indicator in the aircraft that uses the pitot tube. The vertical speed does not, and the altimeter does not use the pitot tube. There's a couple other elements in here. You've got a little heater in case you get into icing conditions. If this ices up, this gets blocked, your airspeed indicator is going to be reading 0, and that could be disastrous if you're in the clouds. So they have pitot heaters. So all IFR aircraft, rated aircraft, are going to have a pitot tube with the heater on it. You can see it back here. There's also some other things here. We've got a drain hole in the back. That's so if moisture does get inside this cavity here, it can drain out the back of the instrument. And then there's also what's called a static port. We'll talk about that in a second here. That's just kind of equalize the pressure in there. So again, this is going to come up. The plumbing is just a tube that runs up to the airspeed indicator. This is again going to be representing the RAM airspeed that's hitting the aircraft. So again, whether the aircraft is sitting on the ground and there's a 40 knot wind, or it's up at 1,000 feet traveling at 40 knots, they're still going to represent the same thing. Okay? So the next one is the vertical speed indicator. Well, actually, before we talk about the vertical speed, let's talk about the altimeter, because that's a little easier. So an altimeter, I do. Okay. So this is a altimeter right here. Let me just. So can anybody tell me what the altitude is that this is showing? 1,000 feet. Yep. And that's because the small dial there, the small needle is pointing at 1. The small needle represents thousands. The long needle shows 100 increments there. Do you see that? So 1,200 feet would look something like this right here. And notice that the small needle is showing still close to 1,000, but that hundreds needle is showing 2. That's how we see that. And then you can't really see. There's a little, very small needle, very thin needle that's pointing up close to 0 there. I don't know if you can see it at all. That's showing 10,000 feet increments, and that's barely reading on here. It's just still pointing at close to 0. So that's how we read the altimeter. But inside the altimeter, if we're to open this up, there's what they call they're like aneroid wafers. Think of the wafers as here we go. This is a good diagram. So these are like little, very thin, fragile wafers. I think they're made out of brass. They're very thin, and it's like a balloon. Okay, you fill a balloon up. So if we take a balloon, we fill it up on the ground, and we raise it to 1,000 feet, is it going to contract or expand at 1,000 feet? It's going to expand. Exactly. That's what's happening here. These aneroid wafers are just a balloon, essentially. They're a more robust balloon. But we take that up to 1,000 feet, and they're going to expand up. And that's going to drive these little linkages here, and it's going to show a higher altitude. That's how that works. So it's an important point. We have to understand, first off, that as we climb up in the atmosphere, if we go, right now we're at ground level here, which is roughly about 920 feet at this building. If we were to climb up 1,000 feet, these wafers would expand, but the air up there has less pressure at 1,000 feet. And the same with 10,000 feet, is a lot less pressure at 10,000 feet. So this is going to affect how this operates. That's how these, an altimeter works. Yeah.
I don't know that you're in there. Is that? I'm sorry, because I know if the airplane is pressurized, how does that goes for?
Yeah, that's a good point. So that's it. Yeah.
Pressurized the same as
Yeah, it's the pressure inside here can't be the cabin pressure, because that would throw the instrument off. So what they do is they have you have pressure that is piped in from the static source of the aircraft. So on a static, let's go back to our main diagram here. There's what's called a static port right here. And this static port is plumbed, and notice they've got some really heavy-duty plumbing going to these, these instruments. And then if you actually look inside an aircraft, they're really heavy-duty tubes on there, because they don't want air leaking in from the outside. So, like in the commercial aircraft, like jets and stuff like that, they're flying at sometimes 40,000 feet. But the cabin is pressurized to roughly 8,000 feet. So they can't have cabin pressure in that instrument cavity, in this cavity right here. It has to be the static or ambient pressure that's outside the aircraft. So again, what they're doing is they're connecting the static port right here that's on the outside of the aircraft, and they plumb it into the case. This case is completely sealed from the outside. So we don't have to worry about cabin pressure leaking into this. Now, general aviation aircraft, we're okay, because we don't pressurize our aircraft. In most cases, there's some pressurized general aviation aircraft. The vast majority of them are not pressurized. So it's just getting that ambient pressure. So curious thing, and we're probably jumping ahead a little bit here, but let's say this gets, this right here, this thing gets, the static port gets plugged up. Is there anything we can do to get this, the ambient pressure into this cavity right here, into this case? If this is all sealed, which it is there anything that we might be able to do to actually get this altimeter to read?
Break the seal.
Yeah, break the seal. I mean, you do that by just breaking the glass. You know, if you're in a, this is if you're in a real dire situation, right? If this static port gets busted, all you have to do is break the glass on one ear instruments. I would probably break it on the vertical speed indicator, because it's a pretty cheap instrument. The altimeter is much more expensive. But if you crack that glass, all of that air that's around in the cockpit itself is static. It's ambient pressure out. It's the same pressure that's outside, maybe a little bit lower, not much, but but it's still at least going to show you what your altitude is on there. So the vertical speed indicator, let's see if we can find one here. Okay, let's just go here. I think again a separate diagram. Let me just see if I can show that here. Down here. Oh, here we go. Yeah. Okay. Yeah. So this. So this is a diagram of a vertical speed indicator. It's very similar to the altimeter in the sense that it's got an aneroid wafer, but there is a difference. The big difference here is there is a calibrated leak, and they don't do a good job of showing it here. Maybe this is a little bit better. And they go into great detail. Yeah, so the here we go. This is a good diagram here of vertical speed right here. So again, you got your aneroid wafers, which again is like a balloon, right? But the difference in this instrument over a altimeter is it's got a what's called a calibrated leak. And the simplest way to explain that would be you've got a balloon, and let's say, has anybody ever done this where you take get a balloon and then you put a piece of tape on it, and then you push a pin through that tape? What happens is the balloon leaks very slowly. It doesn't just pop. If you want to try it sometime, just basically blow a balloon, take some masking tape or something like that, tape it over part of the balloon itself, and then take a pin and push it through it. The balloon won't pop. It will leak air. Okay, that's essentially what they've done here. They're leaking air out of the system. So if I take, let's say we do this with the balloon, does that make sense what I'm explaining there with the balloon? It doesn't pop if you just put tape on it. You've got a nice tight seal on it. It's a very, again, it's a pinhole leak. But if you take that balloon, let's say we blow it up on the ground, or yeah, better way of describing that. We blow it. Let's just say we blow it up on the ground, and then we push a little pin through it. It's leaking air. As you climb, there is, obviously that balloon, if it was sealed, it would just keep expanding, right? But this one's got a calibrated leak, so it's going to keep, getting smaller and smaller. It's just going to leak. Eventually, if we just stay at a certain altitude, the balloon is going to collapse all the way down to nothing because it's got that leak in it. That's essentially what's happening here, but it's very precise. So what's if you're at the ground, let's say you're not climbing or descending, this is going to be reading 0. And right now it's reading about 2,500 feet descent there. But if we start changing our altitude, as we do in the simulator here, so let's go back here. So let's take a look here. So we're seeing a descent there. Because the outside air pressure, the ambient air pressure is changing, it's causing that balloon to expand and contract. So let's go here. So we'll go ahead and climb and watch our vertical speed indicator. Also notice that with the vertical speed indicator, it doesn't happen instantly. There's a little bit of a delay there. So if I pull up, see how there was a delay there when I pulled up? Watch the difference between the attitude indicator. Just look outside here. So I'm flying along straight and level. let's see, first off, let me just get to a, so if you look at your vertical speed indicator, now we're roughly at 0. We're not climbing or descending the sun there. So watch what happens. I'm going to pull up really fast. Our attitude indicator and our altimeter are going to show instant responses to this, but the vertical speed indicator is going to be, there's going to be a slight delay there. See, it's just like a second or so, not much, but there is a slight delay. That's one of the drawbacks with the vertical speed indicator. But your altimeter is going to show an instant jump in that. So if I, let's see, let's try again here once. Oops. So there's always going to be a slight delay in your vertical speed indicator. It's not much of a delay, but it's enough that you should be aware of it. Whereas your altimeter is going to show it pretty much right away. You're going to see that. So this is a 500 foot per minute climb right now. That's about 500 feet per minute right there. If you look at the vertical speed, it's going to 1,000 foot per minute. Once my angle of attack is getting higher right here, right there, so something like that area there. There's about 1,000 feet per minute right there. I hold that attitude there, we should stay at about 1,000 feet per minute. I mean, have back as we get higher there. All right. Does that make sense with the vertical speed indicator? Okay. So again, it's got the difference between that and an altimeter is it's got a calibrated leak on it, whereas the altimeter itself does not have a calibrated leak. It's totally sealed. If you look at that, it's very tightly sealed. There's gaskets in here, and it's completely sealed off from the outside air. So that's how you can deal with, like pressurized aircraft. All right. Let's go here.
Is the static port like in the engine?
It's good question. Let's go back to our simulator and I'll show you. On most aircraft, it is on the outside of the aircraft. It's usually, let's see if they actually show it here. Let's see here. Usually the static ports on most planes are, yeah, we can't see it because the logo here, but there's usually a port on one side or the other. It's usually outside the aircraft. And normally on some aircraft, it's in the back. You'll see like a little tiny circle back here. And it's just, again, it's flush with the aircraft. It's almost unnoticeable in most cases. You look at a plane, you won't even see it there. It's not pointing into the relative wind. It's actually just isolated. It's I know it's on this plane someplace, but it's probably buried in the graphics here. And probably in this aircraft is probably somewhere around here. And it's just going to be a small. You're not going to even notice it because it looks like it just kind of meshes in with it. Excuse me. But what it is essentially just a tube that faces 90 degrees to the relative wind, and it's just picking up.
Right. Look up right above your mouse.
This right here.
A little higher. Almost on top of there.
Oh yeah, no, that's the oil for chicken oil. No. It would probably be in most aircraft. It usually is going to be somewhere in this area right here. The back of the hulls. It won't be in here. It'll actually be in this area right here. Just yeah. But in any case, it is on the aircraft. It's just we're not seeing it here. I'm not sure why it is, but it would be like in this, probably somewhere in this area right here. They're very small. Again, you're not gonna. It's very hard to notice. Let's go here. Let's see. We've got photos of it here. All right. Um, and directional gyro. So now let's, so we've looked at the airspeed indicator. We know how that works. The altimeter, we know how that works. Vertical speed indicator, we know how that works. Now there's the other instruments that we have. We've got the artificial horizon. We've got a directional gyro. We've got turn coordinator. You kind of explained what they do, but how do they work? So to do that, what I'm going to do, these are all gyroscopic instruments. These three instruments have gyroscopes in them. So we've talked about this before with gyroscopes, how they work. I'm going to try to get this thing spinning so you can actually see it, how it works. Do you remember that we talked about gyroscopes a while back? We talked about rigidity in space or rigidity in space. And because of the way gyroscopes work, they resist change. They don't. When you try to move them, they resist. They want to stay in the same position or whatever. And we use that in aircraft, like here for the attitude indicator. That's got a spinning gyro. It actually would look very similar to this. So like, I've got an attitude indicator here. Let's get this thing up to speed here. Okay, so, all right, so let me just turn this over. So if my hand is the plane, just get that from there. My hand is the plane. I can bang up and down, and notice how the even though I'm pointing down, the gyroscope is staying perfectly straight up. It's not moving. It's processing a little bit. That's why you can see it wobbling there. So if I bang to the left, that'd be my plane right there. If I bang like this, that gyroscope is going to stay at that same relationship to the ground. So it's showing what the horizon would be. Spin up again here. So that is what is inside the artificial horizon right there, the AI, your attitude indicator. They're all the same thing there. And it's just basically it's the exact same representation of this, except that it's using a vacuum system to draw air across like little veins in that thing that's that wheel that's spinning there, and then that creates stability for it. Okay. Let's try this again here. So this time I'm going to actually put it right on the plane here so you can actually see it. So if we're flying this aircraft right here, if I go into a bank, it's going to see how it stays perfectly straight there. It's exactly what your attitude indicator is doing there. It's showing that. If I go into a climb, same thing. It's just trying to stay level with the horizon. So that's how we use a gyroscope for your artificial horizon. Now, the other one that you can use it for, let me just try this. I'm just going to set this on here, is your directional gyro. So what we're going to do now is we're actually mounting that wheel vertically like this. Now watch what happens when I turn it. This is always going to point in that direction. See how it's always pointing to that wall. It's moving around a little bit, but this right here is always pointing to that wall. That's how the DG works. And with your turn coordinate, it uses basically the same principle on there. You can see now it's starting to process a little bit. So, and keep in mind that in a real aircraft, these they're constantly spinning at like 20,000 RPM. They're spinning very fast. This is only maybe like 10,000 RPM is what I can get up to, and maybe the batteries are dying on it. I'm not sure, but that's essentially how gyroscopes help us fly. So I can take it like that. Notice how that is always pointing over there, right there. As I turn my aircraft, my hand representing the nose of the aircraft. There, I turn around, it's now starting to process a little bit there. But the whole idea here is, we need to have these instruments. So if we do, go into the clouds, or we want to do real precision flying, we can use those flight instruments to help us with that. So does that make sense? Again, that's the attitude indicator. These are the gyroscopic instruments right here. Whereas the whiskey compass, we call it whiskey because back in the old days they used to fill it with really with whiskey, and that was to dampen the movement of it. But here you can see that dial under is just moving all over the place. I'm just barely moving it, and it's shaking around. You can't really trust this in flight unless you're in smooth conditions, not accelerating, either climbing, descending, or in a turn. But anytime you're in some other condition, the compass is going to be very difficult to read. Whereas a directional gyro, we can see how stable that is. So let me just this. And look at how it's stable here. I'm just going into a turn right here. So see how smooth that directional gyro is there? It's just showing a constant turn. One of the drawbacks, this I'll get to in a second. So one of the drawbacks with the gyroscope, we saw it here, was that they have a tendency to precess. I think we talked about that before about precession, where if there's any friction in the system, this is going to start doing things like this. It's going to wobble and stuff like that. So that can happen with any of these instruments, but mainly with their directional gyro, just because of the way they're designed. Because there's some friction there, this is going to start going. It's going to start indicating the wrong direction. So what we do is we reset it. So let's say what I would do here, like in flight here, I would look at my compass. Well, first off, I'd fly straight level. And then look at my compass. Okay, we want to stay fairly stable here. So right there, we're about, let's right there. So it's about 20 degrees right there. So I just pause this. So what I would do is go down to a directional gyro and adjust it. So let's pause it here. So I grab this and I can just turn this. This adjusts the dial there to what our heading should be. So now I get out there. But in any case, that's how we correct the precession in a directional gyro. And you have to do that in some aircraft. You have to do it every 15, 20 minutes. Most aircraft, if you're not doing any like steep turns or anything like that, a long straight course, you may only have to do it once an hour or so. But it is something that you have to be aware of when you're flying. And it's simple to check for. You just look at your compass. So look at your compass, what your heading is on your compass, and then compare it to your DG. If it matches up, then you don't have to do anything. Okay. Easy, good question.
So exactly the compass was just compass.
Why we have a compass? Okay, so the reason why we have a compass is because we don't know where magnetic north is without it. We can't. What's that?
Why would be
so if you want to go from let's say Baraboo to Madison, okay, so it's about 135 degrees is what you'd want to fly. We don't know what to set our DG to. We don't know where north is, on our directional gyro. So we'd have to, before we take off from Baraboo, we'd have to set this to magnetic north. So that we know what we're going to, because this could be, we could set this to anything. This could be adjusted to east, west, anywhere we're at. This is not receiving any information from the outside world. So this compass ties us to the rest of the world and say, okay, well, this is the direction that you're pointed in, and on the ground, this is going to be pretty stable. It's going to show the magnetic heading of when we're on the ground, whereas the DG is just it's whatever we set into it, if you land and somebody tows your aircraft to a totally different direction, you'd have to reset your DG. And if it spins out, the plane is off, the gyroscope stops, whatever, again, it's going to be showing the wrong direction there. So that's why we have to have a compass. And it's required on every aircraft that you have a compass. So you can navigate. You don't always have to have a directional gyro and some of these other instruments, but you definitely need a compass. And that's so that you can navigate. from one location to another. So like at Baraboo, I'd take off and I'd fly 130, basically in the southeast, about 135 degrees, something like that it is. And that would take me to Madison, but I can't rely on my DG for that. Right. All right. Let's see here. So let's yeah. So the reason why we need to know all these things like pressure and everything like that, like altimeter, the reason we have to know what the altitude is because you know, there are towers when we come into land that we want to avoid and stuff like that. So if somebody says, hey, there's a tower south of Baraboo that's at 1,000 feet, you know, above the ground, we need to know that so that when we come in, we stay over 1,000 feet on here, and we use our altimeter to tell us that. Now, some of the things that happen, and we've talked about this a little bit before, but some of the things that can happen is you have changes in pressure in the atmosphere. So here we've got, yeah, so here we've got an area, let's say this is Reedsburg right here, you've got relatively high pressure and then lower pressure at Baraboo. And notice that both of these planes right here, let's see that name. Yeah, these would yeah, they're both. We'll use this right here. All right, so at Reedsburg, you know, maybe you've got relatively high pressure. Let's say like this put it in a better diagram. Oh, by the way, this is what a static port looks like. It's just on the side, very small. It's maybe like this big on there. You'll see it even on jets. They're very small ports there. And then this is your typical pitot tube right there facing into the basically points in the same direction. See if we can find a diagram that shows it better. Yeah, Donnie.
Why does the pitot tube have to be like 6 inches or 3 to 6 inches? It's like away from the
Yeah, it's a good question. What happens with so right here, this is the leading edge right here of the aircraft right there. So this right here is the leading edge, and the air comes in from this direction, flows over the aircraft like this. But the problem is when air is flowing like this, it hits this, it creates, you know, turbulence in this area where that, you know, this pitot tube kind of extends down right here. And so what they're trying to do is they're trying to get that out of the turbulent area there, so you get a more accurate reading of what the ram area is. So in supersonic aircraft, it's even more critical. And I don't know if you guys have ever seen like pictures of some supersonic aircraft have their pitot tubes stuck in a hole. What's that? Yeah, they put it on the nose. Yeah, and sometimes they'll put it way out there. Yeah, it's way out there, and that's because there's a lot of turbulence around the aircraft.
Find that on like the one or something.
Oh yeah, that was the one that had a long. Yeah,
I remember seeing, I think Worst or something, like one of the first jets to go supersonic ever had a chip really long.
Yeah, because they were still experimenting with it then. They didn't know why they had to do it, but they just know that they had to do it.
Measure the opening from Chinese.
Oh, really? I didn't know that. Yeah, that's fascinating.
Yeah, I've seen that. I got to see that for SIA.
Okay, so
They didn't have it, so.
You got it here.
Maybe it's slightly more similar.
There's no way the limbs should be on.
It was easy.
So let's we'll get back to here. So let's say again, atmospheric pressure is going to affect how our altimeter reads. So if we have relatively high pressure, our altimeter is going to read, different than if it was at, an inch lower. So, yeah. Okay. So we're talking about this a little bit before that. There's a little window in the aircraft or in the altimeter. It's called a Colesman window, and that's for adjusting the standard for adjusting the altimeter to whatever the current pressure reading is. So, and you'll notice here as I turn this, that those dials there kind of move there. You can see that at all. That's adjusting it. So if I'm standing out on the ramp here and I have an altimeter, what's the best way for me to, like, I don't know if this is reading right. I know what the altitude here is. What's the best way to set this to temperature? Set?
Radio call to ABC to get the barometric pressure.
You could do that. You could do, yep. And what else? AWAS, yep, because they'll always be reporting the current barometric pressure, the altimeter setting, we call it, or the barometric pressure for the airport. Another thing we can do is, well, I know I'm standing at 920 feet. So I can just turn this to 920 feet. That's the other thing I can do. That's something that doesn't change. Our altitude here is fixed. Unless we have an earthquake and we sink or rise or whatever, it's always going to be 920 feet at this point. When you're up in the air, you don't know what it is. That's why we need to get hold of ATC and ask them, or listen to AWAS or ATIS or something like that. That's when we use the Colesman window here on this side right here. We adjust it, and it's hard to see. Let me just see if I can bring it up on the here. So zoom really close here. So it's 29. Can you read that? 29.9. Zoom a little bit more. And here it's kind of hard to see here, but that says inches of mercury there. So on this side, we've got 29.9, 30 inches, 30.1 inches, and so on and so forth. So you can actually adjust your altimeter with this knob, this right here, will adjustments. So if I, here we go. If I change that, see how it's adjusting that window there? That's what you're doing. You're adjusting it for whatever pressure you got there. And again, that's based on the altimeter setting. That's the pressure setting outside. And that corrects your altimeter so that we know that we are at that altitude. Jason did mention that, I think it was Jason, that you said it's measuring the height above sea level, not above ground. It doesn't know how high the ground is below you or where it's at below you, but we use the sea level as a standard reference throughout aviation in the world. We use that because it's pretty much standard. You're always going to have the same sea level. It's always going to be zero, roughly. So we use that as a kind of a standard reference for it. So your altimeter is always going to show that. You may have terrain that rises up 2,000, 10,000 feet, and your altimeter may say you're at 12,000 feet, but your height above ground is only 2,000 feet. If you're flying over the mountains, and your altimeter says 2,000 feet, your mountain right here, even though you're at 12,000 feet on your altimeter, you're only 2,000 feet above ground. So again, that stuff is really important because if you run into bad weather, you can't see outside, there's towers outside, geographic features you can run into and things like that. So you obviously want to know what your altitude is there. Okay, so a couple things too they'll point out. When you go from high pressure to low pressure, they've got a term that will help you remember this. And if you think about how the atmosphere works, you should be able to work some of these problems out. You will see these on the exam to talk about what pressure affects, how it affects the aircraft itself. But so there's a saying, going from high pressure to low pressure, look out below, or going from high to low, look out below. That's a common term that we think about. So what they mean there is if you're going from area of relatively high pressure, let's say you're on a long cross country, you're going from Madison to Duluth or something like that. And the pressure in Madison is 30.1 and the pressure in Duluth is 29.1. That's a 1 inch difference. That's about 1,000-foot difference. So for every inch of mercury, you're talking about 1,000 feet. So from high pressure in Madison, we're at 30.1. Now we're flying into an area of low pressure up in Duluth. They're showing a pressure reading of 29.1, let's say. So because you're going into lower pressure, the altimeter is going to actually indicate lower than you actually are. High to low, down to low. So as you climb, you go from Madison, say Madison's right here, and Duluth is over here. And even though your altimeter is always reading, let's say you're at 3,000 feet, it's your actual aircraft. If you stay at 3,000 feet, you're looking at your altimeter, 3,000 feet, it's actually going to be descending down quite a bit. When you get down to to Duluth, you'll only be 3,000 feet above ground. You'll only be like 2,000 feet above the ground if you're at 3,000 feet above the ground in Madison. So that's again one of those things that affects how we use the altimeter. So you're constantly setting your altimeter, setting that Colesman window. We're constantly adjusting this during our flight, and we should, especially when there's frontal changes. There's a high, strong high pressure or strong low pressures, more stronger low pressure systems moving in, because they can move really fast and they can change the pressures quite a bit. So again, important to understand how the altimeter works. High to low, look out below. That's very simple to remember and commit it to memory. Also, from hot to cold, look out below. So hot air, if you're flying from relatively hot air into relatively cold air, again, we're flying, let's say, back now from, or let's say we're going again going from Madison to Duluth. If let's say you have your altimeter set at 3,000 feet at Madison, and you're flying to Duluth, temperature at Madison is 90 degrees, and Duluth it's like 60 degrees. There's a big temperature difference. Well, if you don't change or adjust your altimeter, the aircraft is going to again show lower altitude. Right? You'll be flying at a lower altitude. The altimeter is still going to say that you're at 3,000 feet. So those are the types of things again that we have to be aware of with it. So they talk about, they've got some diagrams in there. I think this here. Yeah, this one is a good one for showing the effects of non-standard temperature on an altimeter, what it does to the aircraft itself. All right. Tell you what, let's take a quick break and then we'll jump back into this here, and then we're going to just we should be able to finish this up. The rest of this stuff I think is very straightforward here. Yeah, they talk about some of the things we've already gone through here. So let's take a quick 10-minute break and then we'll dive back in it. Does anybody have any questions so far?
So it's like a Garmin system, like program itself, like parametric pressure.
No, I mean it's well, I guess it depends on the system that you have. I mean, if you've got a more advanced system, there's some things that can automate, but you're still going to be putting in your barometric pressure, on a Garmin unit. Whether and that's just one of those things that's you have to get it from the ground. You have to get the barometric pressure reading from a ground station someplace, because that's going to tell you where your altitude is at. Let's see, when you get to ground, which is the most important thing. If I know that Baraboo, let's say, is at 980 feet, I'm landing there, and I'm coming in clouds and stuff like that, I would need to know that I need to have that set on my altimeter. And there's no way for me to figure that out at the altitude that I'm at, because I'm up too high, and you've got non-standard temperature or non-standard pressures. You'd think that the pressure would be fairly consistent as you go up. It's not. It changes in the atmosphere. It obviously goes, the pressure drops as you climb, but it's not always consistently dropping. It's, if you've got a strong, pressure system or a weather system that's moving in, it may have what's called non-standard blast rates and things like that. That's why we can't just stick an instrument outside the aircraft and get the actual barometric pressure. We just don't know what it does. So now they do have radar altimeters. That'll help. And if you've got a radar altimeter, you can, get a fairly close approximation of what your altitude is. But it's, again, it's best just to get an altimeter reading from an AWOS or ATIS or something like that, because that's going to tell you exactly where, what your altitude is at. And then plus everybody else that's flying around has that same altimeter setting, so they're going to be flying at the same altitude. If ATC gives 2 aircraft, one altitude to fly at 1,000 feet, the other one 2,000 feet to fly at. They want to know that those guys are on the same page. They're using the same reference, the ground reference. Otherwise, they could be flying at the same altitude and flying. Right. All right, well, some of you guys going to keep going. Let's just keep moving here on here. So on page 8.6, they talk a little bit about the types of altitude. There is indicated altitude. Whenever you hear the term indicated, it means that you're reading the whatever it is off of an instrument. So if you hear the term indicated, that means that you're reading off an indication in the aircraft. So in this case, this is the turn coordinator, maybe a good one, but the altimeter right here, it's indicating, this basically 920 feet on here. It's essentially what that's indicating. Airspeed, again, same situation. Let's see this here. So, this airspeed indicator is presently indicating 0. The reason why we have indicated as opposed to some of the other ones, they've got to talk about calibrated and some of the other types of speeds there, is because there are certain errors that are built into like instruments, and you may not, even though it says it's 100 knots, it may not be actually 100 knots that you're traveling in. So with an airspeed indicator, and the same with the altimeter there. So again, let's talk about types of altitude. Indicated altitude, again, read directly from an altimeter. True altitude, the vertical distance of the aircraft above sea level. So this is your actual altitude above sea level, or MSL altitude. And then absolute altitude is always the distance above terrain. So sea level is about another 920 feet below us at this point where I'm standing. If I were to drill down to the ground 120 feet, you'd be at sea level. With absolute altitude, we're showing that that's how high we are above the terrain. So if I'm at right now, if I read on my altimeter and it's set correctly, let's say I climb up to 3,000 feet, and let's say the field elevation here was 1,000 feet, we'd still be at 3,000 feet here. Show indicated 3,000 feet, but I'd only be 2,000 feet above ground. Okay, that's the difference there. Absolute altitude would be 2,000 feet. Indicated altitude would be 3,000 feet. True altitude would be 3,000 feet because everything's set up. And pressure altitude, that's essentially indicated when you just turn your Colesman window just to a standard temperature or pressure setting of 29.92. That's what, and we're going to use that for doing calculations of performance and stuff like that. a lot of performance calculations require the current pressure altitude. Let's see, and then density altitude, that's another one. That's going to be pressure altitude corrected for variations from standard temperature. So we get into this a little bit more too in the weather when we start talking about weather and doing basically like long distance navigation. We talk about the effects of these on the performance of the aircraft. So I won't go into a lot of detail here. Let's go here. Okay, so on 8.8, they go into the airspeed indicator. They talk about the airspeed indicator. So again, you have indicated airspeed. That's what you're reading off the dial. You also have what's called calibrated airspeed. This is on 8-9 now. Calibrated airspeed, which is indicated airspeed corrected for installation error and instrument error. And you know, when you look at an aircraft, you've got a pitot tube. Let's say we've got a pitot tube hanging off this aircraft right here. It would make sense that it's most accurate when the plane is down low to the ground, you know, flying straight and level. But if the aircraft is at a high angle of attack, let's say, and flying like this, that ram air now is not all hitting that vertical or that pitot tube. It's if I fly like this right here, the pitot tube's pointing up, and here it's pointing straight ahead. So if I'm flying like this, for instance, that pitot tube is picking up that ram air. Again, if I go into a high angle attack, it's not getting that direct ram air. So that's the difference between, you know, the indicated and calibrated. So again, with certain changes there. And then true airspeed is corrected airspeed, calibrated airspeed corrected for altitude and non-standard temperature. The ground speed is literally that. It's the speed of our shadow across the ground, which may be different in some. And I hear guys, it happened to me several times. But basically, you take a plane up on a really strong, you know, where you've got a lot of winds in that day. You can literally take it off, and if you point the aircraft into the wind, you may actually be flying backwards. You know, at a high enough. If you get high enough and you have strong enough winds, the plane will fly just fine because it's moving through the air around it is relatively, it's moving fast, maybe like 100 knots or 60 knots or something like that. But because the wind is so strong, it's actually moving it backward. It's a really weird feeling, but that's the distinction between ground speed and, you know, your airspeed. Again, airspeed is how fast you're moving through a parcel of air. Even though that air might be moving around you, you know, on this, it's affecting the aircraft there. And it's important to understand the differences between, you know, ground speed and airspeed. Okay. So I think we've gone over this. I'll just show it to you again here just to go and be on the safe side here. All right. So airspeed markings. So there are several that are on here. We talked about this in the past. DSO, that's a stall speed with flaps out, everything basically hanging out, flaps out, gear down, things like that. DS1 is the V, by the way, stands for V, speed or velocity. So these are all V speeds on the indicated on the airspeed indicator. And every aircraft is going to have something very similar to this, depending on the performance. But they'll always have white arc, green arc. Sometimes they'll have a yellow arc and a red arc there. So these markings always indicate the same things. Again, white arc indicates the safe flap extension speed. In the bottom of the white arc is going to be the stall speed on there. The green arc is going to be the aircraft in a clean configuration, and the stall speed right there, DS1. You can see it's listed right there. White arc, again, it's there. Top of the white arc is indicating the maximum speed that you can have the flaps out. So beyond this, if you fly the plane with the flaps down, there's a possibility you could overstress the flaps and break some linkages or something like that. It would be unlikely that it is possible. But you will, you know, at some point, if you're flying long enough, you'll actually start warping the backs of where the flaps are attached. That's almost a guarantee, and you can see it if you look on the aircraft where somebody's flown flaps out. You'll see stress marks on the skin there. The green arc is a normal operating range for the aircraft. Essentially, you can fly basically anywhere in that area, that region, and control the aircraft. And then yellow is the caution range. So you typically don't try to fly in really turbulent air in this yellow area, just because the faster a plane is moving, the more stresses you're. So if you're flying at 140 knots in this, according to this diagram right here, 140 knots, if we hit a lot of bumps, it could overstress the aircraft. So, and then the red mark that's the red line. We've talked about this before. If the aircraft goes beyond that, you're essentially a test pilot. But what can happen is the lift that you're producing is so strong it can actually warp the wings. So that's why they have a red line. Normally, when you're flying straight and level, you'll never even come close to that. But if you point the aircraft down in a steep dive, you could easily surpass that. The red line never exceeds speed. That stands for head. And here's another one right here. Okay, so those are all collectively called V speeds, by the way. There are some speeds that are not listed on the altimeter. The maneuvering speed, landing gear operating speed, they've got them listed on 8-10 there. Best rate of climb speed, single engine, best rate of climb speed. That actually is on there. So, but a lot of times you won't see those other speeds, those V speeds. And this is on page again 810. They talk about the other types of V speeds there. Maneuvering speed, you won't see that VA. That's an important one, just because of the way the physics of flight. You can't. It's not. The maneuvering speed is constantly changing based on how high you are, what the density of the atmosphere is. So it's going to actually change a little bit. We'll talk about that. So they go into the blocking a pitot-static system. What can happen if the pitot tube is blocked. So in the case of this, all right. So if you've got a blockage in your pitot tube, can anybody guess what's going to happen to the airspeed indicator? Yeah, it's going to show 0. Yeah, because there's no pressure, nothing blowing through this tube and to hit this and cause that needle to move. So that's simple. But what can also happen is you can also have a static blockage going to the airspeed indicator. And this is not as intuitive. So
It's a static port, just like a back there.
no, it is not. What it is, the cavity inside the
There's like for like everything, but like kind of for the actually.
it's not going to show you. It's not going to indicate any airspeed at all. If that's what you're asking. Yeah. So what happens is you've got this airspeed indicator, as all airspeed indicators, you're going to have 2 ports. One is going to be the ram port from the pitot tube itself, this one right here, and the other is going to be for your static port. So the ram port goes in and it fills. I'm not sure if it's like some sort of weather vane or something like that, but it actually impacts something and causes that needle to move. The static port is just filling the outside or the air surrounding that with the air that's outside, the static air pressure that's outside, or the ambient air pressure. And that's so that this reads accurately at any altitude. If this was completely sealed off, this instrument would not really read correctly. It'd have to have the outside static pressure in the instrument itself. So when they talk about that here, how that works. So blocked pitot system. Okay, we know that. Let's see. I think they talk about it here. Block static system. Okay, yeah, on 811, 8-11. If the static system becomes blocked, the pilot pitot tube remains clear. The airspeed indicator continues to operate. However, this is where I was saying before, it becomes inaccurate. It is inaccurate. The airspeed indicates lower than the actual airspeed when the aircraft is operated above the altitude where the static ports became blocked. So this is where you have to use a little bit of judgment, I guess. You have to think about what's happening inside of it. I don't know that you see any questions on there, but you do need to know that if the pitot-static system is, if the pitot tube is blocked, obviously it's not going to show any airspeed. And if the static system's blocked, that's going to show different errors when the aircraft descends or climbs. Yep.
So you could tell if the static port is blocked, even though the airspeed would look like it was still moving. Tell if it would be incorrect because we would see other instruments would stop working. So that would tell you.
Yes, yeah. So if the condition of the aircraft changes. So if let's say I'm flying along at 1,000 feet. I'm glad you brought that up. So let's say I'm flying along at 1,000 feet and somehow something happens. Ice covers up the static port, not the pitot tube. The pitot tube stays open, but if the static port gets blocked, and we keep flying at, let's say, 3,000 feet, nothing changes. Everything is correct. It's when we start climbing or descending that we're going to start seeing errors. So if the static port gets blocked at 3,000 feet and we start climbing, what is that going to do to the altimeter? Is the altimeter going to show a descent, a climb, or is it going to stay the same? It's going to stay the same. Yeah, because that static port is blocked. All right. So now let's think about the airspeed indicator or vertical speed indicator. What's going to happen with that? It's going to stay zero. Yeah. It's let me think about that. Static port gets blind. Yeah, because it would be reading it in there. Yeah, it wouldn't affect it. So it stayed zero. So that would be your telltale signs. You've got a block static on there. And then the altimeter, obviously, or the airspeed indicator, is going to if you're at a high altitude and you block your static ports, the static pressure inside the cavity of the airspeed indicator is going to be the same pressure that the static port was blocked at that time. So if let's say the static port was blocked at 3,000 feet, and I go into a descent, the airspeed indicator is going to act as though I'm at 3,000 feet, essentially. That's the way to think about it. So when you see a question on the FAA test, if the static port gets blocked, how is it going to affect the airspeed indicator? It's when it gets blocked, it's going to remember that what your airspeed is at that point. So yeah.
What blocks them like a static port or like a?
I'll give you anything on the ground. When you do your pre-flight inspection, you're going to walk around the aircraft and you're going to look for, like, dauber wasps love to go into pitot-static tubes. You can get ice in there. Bugs can smash into the pitot system, not so much the static. Somebody can wax your aircraft or paint your aircraft and cover up the static port on it. They're tiny. They're little, smaller than like almost like a pinhole is what a static port is. So it doesn't take much to block up chase.
Yeah, usually when they're washing a piece of tape or the static, so there's no water with it.
Mm-hmm.
Those pieces of tape I've had on actually.
Mm-hmm.
I caught it thankfully, but it was really hard to see that piece of tape.
Somebody actually left it on there?
Yeah.
Oh,
After they were done cleaning. It was really hard to see.
Yeah, that's the kind of things that can go on in real life. So that's your job as pilot and commando. You have to walk around the aircraft and inspect all these things You have to know what to look for. And Jace, caught this when he was doing his inspection, right?
Yeah.
When you're doing a pre-flight. So when he walked around the aircraft, he saw that piece of tape. Could have been a bug, or something like that, whatever. But you have to. That's your responsibility when you walk around the aircraft. When your instructor takes you up flying, they're going to expect you to do the pre-flight, and they're entrusting you with their lives that you're going to inspect things like that. That could be a serious problem.
Yeah.
So if you guys would have gone up, let's say, and the instructor said, okay, well, let's do a quick IFR flight plan, and we'll fly over to Green Bay or something like that. And you hadn't checked that. That could have been serious, very serious. So oftentimes instructors will back up the students. They'll do their own little check for critical things, but at some point they're going to trust you with their lives. So it's up to you to check the oil and things like that in the aircraft. Okay. All right, so let's go here. So electronic flight displays, we kind of talked about that, how they work. So I'm not going to delve too much in that. If you guys have questions, then let me know. But essentially, they do the same thing. I'll just back up out of here. Let's just do this. Let's go here, configuration, and then I'll do the G1000. Just so you can see how the PFDs and the MFDs work. So PFD, by the way, stands for primary flight display. That's your primary flight instruments, which we just went through the 6-pack there. So here is our, I just want to get this thing up in the air here. So let me just. So I've got a large display here on the left-hand side here, right here. You can see that. That's our primary flight display. It's the same thing as this right here. And I'm going to pause just for a second here. So watch this tape right here is our airspeed tape. You can see that it's increasing there. And also when I rotate, watch your altimeter right here. That's going to show you how fast it's climbing. Directional gyro right here. Again, it's synthetic, so there's no spinning gyros in these things. They're all solid state electronics, and they calculate all this stuff without the the need of a gyroscope or whatever. But it works on very similar principles. Okay, here we go. So I'm going to rotate. Watch my altimeter now. That altimeter tape is going to start to climb here, so there we can see it. We can see our vertical speed indicator there. Just pause again a second. So here's our altimeter. So right now we're just, and this is out of Reedsburg here. So we're at 1,020 feet. There's our vertical speed right there, 500 feet. And then our current airspeed is 61. And then our heading in this case is south. So we're heading someplace south. So everything's all right there, and I'm not coordinated. There's that little, that represents the ball and the turn coordinator here. So that means I'm not applying enough rudder pressure on the one side. That's that little, see how that dash right there is off to the side? That's I'm yawing incorrectly in the lane here, so I'll try to center it here. Try to get that centered. See how that line where the most pointer is right there? See how that moves back and forth? It's basically it's that ball. So I'm going to yaw drastically to one side here, and see how that line now is all the way to the right. I'm going to now yaw to the left. So right now I feel like the plane is throwing me this way. Right, yaw to the other direction. I've got full left rudder right here. And it's yawing in the other direction there, and you can see how that is lining up. So that's what that indicates. A lot of times pilots don't even look at that, but that's very important. It tells you the quality of your turns and stuff like that, and where the center of gravity is. So, right. So that's how a primary flight display works. You've got your altitude, your airspeed tape, altitude tape. You've got your artificial horizon right here. You can see how this works. That little center line, this right here, is just a reference arrow right there, and those yellow marks there on the side. Those help us line our aircraft. Now, if I want to fly it straight and level on the horizon, I just put right there essentially. or something like that. Very well, but, so that's everything. There's all 6 instruments built right into the primary flight display there. So, okay. Great. So actually, let's look at our engine instruments. So those were all of our flight instruments. You can see that on the page here. Most of the more advanced planes now have 2 displays. They'll have one for navigation and another one for engines and with instruments and things like that. And I'll show you that here in a second. Here. So, and there are different types of systems. What I've been showing you so far, this is a typical representation of like a Garmin G1000 output there. You can see how it looks like it's got the same kinds of buttons there. They're all very similar, but there are other manufacturers out there. It's not just Garmin, and sometimes they have different interfaces to their systems there. But they all have several things in common. You'll always see an airspeed tape on the left-hand side and altimeter on the right-hand side. They all have different representations of vertical speed. So here, like in this one, they've got almost a dial here. I don't know if you can see that. I'll zoom in here. This is the representation for minus 500 foot descent is what that's showing here, the dial there. And that's on 814 there. So again, this is from another, Shelton's Flight Logic top. So Avidyne, Integra, another one. Oh, this is the Avidyne Integra. So this, yep. It is. Yeah, good observation there. So that's, again, it depends on the manufacturer. A lot of the newer G1000 systems have synthetic vision, where they actually, it's literally like flying a flight simulator. When you look at it, it has all the same stuff that they have as a regular flight simulator. So, if you do run the clouds, you actually could get to your destination. It's not a good idea, obviously. If you're on an IFR flight plan, it's brilliant. It helps for what we call situational awareness for the pilot. They now understand where they are. They can look at a monitor and fly to it just the same way that we use it to fly a flight simulator. So, and those systems are extremely helpful. So this one right here, no train. This one does have train, and it's very basic. These synthetic vision ones are really good. They're like on par with the flight simulators. If you were to actually fly a flight simulator up there, it would be like flying a flight simulator in a real aircraft. You'd actually see all the real terrain and stuff like that. Data computer. So yeah, there's always some unit that's doing all the number crunching and figuring everything out. They're typically called an air data computer, and usually they're in the electronics bay of the aircraft, usually in the back of the tail of the section of the aircraft. Not always, sometimes they're up front. It depends on everything is getting so small these days. The computers and stuff like that, now they can put everything in one solid unit. Whereas in the old days, look at how big these instruments are. This is hefty. This is probably weighs about a pound, maybe 2 pounds. This is what we had to fly with. Nowadays, it's as light as that laptop that should have all these instruments now are now basically the weight of a light laptop, and not very heavy at all. Okay, yeah. So that's another thing too. They do show trend lines, and again, I don't know if you'll experience that in there, but let me show it to you anyway so you can see it. So what I'm going to do here, let me just make this nice and large so you can see it. there are these things called trend lines on these multifunction and primary function displays, or PFDs, FDs. So what I'm going to do, I'll unpause it here. But what a trend line is, it extends up from basically the center right here, and it goes up. It's a magenta line that goes either up or down, and it shows that there's a change in the rate. There's a rate of change in your speed or your altitude. So you may be climbing. Let's say you're flying at 80 knots, which we are right now. If your rate is changing, let's say you're increasing your rate, it's going to show it on here. So let me show you what this looks like. Well, maybe they don't represent it on here. They don't.
There's one.
Okay, okay, so let me just pause here a second. All right, so this right here is the magenta line I was talking about. So that's showing a rate of change increase. And so we're increasing our altitude. That's what that, if you just glance at it and you see that magenta line, that means that something is changing. In this case, it's on the altitude tape, and it's showing an increase in the altitude. There's the center right there, and this is going up in this direction. Conversely, if I point the nose down, this little magenta line is going to point down. That indicates that there's a trend down. Okay, so let's do that. So let me just point this down. We have much room to spare there. Now you can see it going down there. See it? So there's our downward trend right there. That's what that little magenta line indicates. And it should, on most of those PFDs, they'll actually have a trend line here as well, but this one apparently is not showing it for your airspeed. Okay, does that make sense? The reason why they have that is because, believe it or not, there's more glance, what we call glance value, in the old dial gauges, the steam gauges instruments. I can just glance at this and I instantly know I'm, roughly 40 knots or something like that. Whereas when we glance at this display right here, we actually have to read the numbers off it. It's a minor detail, but when the task is saturated and you've got all this stuff going on, it does have a tendency to slow you down. Whereas here, just a quick glance, and I can see I'm at a safe airspeed. Here, I have to kind of interpret it a little bit. They do have a lot of different types of representations on here that help, but it's still not the same as looking at a dial on it. It's just super simple. Yep.
Yeah, whenever I was looking at the digital one, I'm just like, this one's so much more going to look at. So I prefer looking at the traditional one.
Yes, yeah. The nice part about these displays, though, is everything is right here. It's all right there. You don't have to glance to another instrument. Your eyes can, if you're doing a cross-country IFR flight, for instance, you can easily, just by looking at it, you've got right across here, you've got airspeed, altitude, and your attitude of the aircraft. And then if you look down just a little bit, you can see your direction. So it's very quick. The problem is it does take a little bit more time to interpret some of that stuff. So there's still pilots that prefer the old steam gauges. They're not big fans of this stuff. I love this stuff. I think it's excellent. It helps with situational awareness, especially that big display with the horizon. You look at the other aircraft that are out there, the steam gauge aircraft. Here you have to interpret at each one of these instruments. And of course, it's a lot easier because you just quick glance at each one of these and you can see what's going on, but it's not the same. This artificial horizon is much smaller. It's, basically the size of one of these instruments right here. Whereas the large PFD display here, this is huge. It helps with situational awareness. Okay. All right, yeah, trend vector. So that's all right. Gyroscopic instruments. We talked a little bit about how gyroscopes work. What we didn't talk much about was precession. That's something that, again, it exists in all gyroscopes. So this is on page 815. Okay, yeah. What precession is, it's okay. The reaction, precession is the tilting or turning of the gyro in response to a deflective force. What they mean there is if this thing is spinning super fast, and there's a force exerted on it, there are because there's always some friction someplace in the bearings up here, down here, whatever. There's going to be other forces that act on the gyroscope, and it's not going to behave the way we always expect it to. And because of that, you do have this precession or tilting of the gyro in response to those forces there. Yeah, another thing, and I think we talked about this before too, the reaction to this force does not occur at the point at which it is applied. Rather, it occurs at a point that is 90 degrees later in the direction of rotation. So, and in that case, let's see, if I spin this like this, and I put pressure right here, it's going to act as though it's being pushed right here. It seems really weird, but that's how gyroscopes work. They always, it's like it's going to affect the, how it works. That's just, again, that's the way gyroscopes function. Again, if you read that, that's on precession there. That's an important thing. You need to understand that. It's the same thing that causes their left turning tendencies in the aircraft, by the way. When we talk about gyroscopic precession as a left turning tendency, it's the same thing. Again, the engine itself is a big spinning gyroscope. And because you've got all this mass spinning, it's susceptible to precession as well. Great. Let's see what other things we got here. Okay, sources of power. This is on H16. We get, well, here, let's talk about this. So this is the turn coordinator. This is actually not powered by the vacuum system. This is powered by an electrical current. And it looks very similar to this right here, by the way. This is a directional gyro right here. And you can see actually as I turn it there, you should see the dial turning there. You can see what I'm doing here is I'm adjusting that gyroscope. So remember before I showed you the gyroscope outside, and I was turning my hand like that, it was always pointing to the south there. Remember that? So that's essentially what they have here. They've got the same setup here. This is mounted on, this gyroscope is actually, if you were to open this up, it would look something similar to this right here. And as the aircraft turns, it's always going to point in that same direction, just like it did when I had my hand out here like this. I was turning it, it was always staying the same. And because of that, because it's always staying in that same direction there, as I turn, it's going to reflect that the correct direction on that. And again, it's just a gimbal. That's all it is. And there you can see there it's moving up and down, and that's to compensate for when you go into climbs and descents and banks. This will always stay. It'll try to stay rigid in space, so it's not moving around there. But they need to do that with the gimbals. They need to mount those gimbals in there so that it can shift around and not change the. It will allow it to change the dial direction. So, but yeah, this one actually is driven by air. Okay, on here I believe. Well, this one I think is electric. Yeah. But in any case, if it's air driven, all they're doing with an air driven instrument is basically passing air over the vein. So there'd be like a tube coming in to the gyroscope that is fed from like a pressure source, or they would have they'd have two ports, one input port, one output port. Normally, for most general aviation aircraft, the output port would be connected to like a vacuum system. It draws in air essentially, and there are veins on the gyroscope. And when that air hits it, the gyroscope spins at a real high speed, like around 20,000 RPM, which is very fast. And it keeps that stable. So there's always air blowing across those veins on the gyroscope. And because of that, you get a little bit more stability. The faster these things turn, the more stable they are. And you notice that when I actually held it up like this, when I first spun it up and held it straight up, it stayed pretty level. But then over time, it started slowing down and started wobbling and processing and things like that. With a vacuum system, you're always causing air to flow across those vanes and keep that speed of the gyroscope at the highest rate you possibly can. So that's how they work. And you can see on this, let's see, what is this? 820. There we go. Yeah, here's a gyroscope with vanes in the gyro buckets, they call them. But there's airflow, the buckets hit it, and it causes that gyroscope to spin. And there obviously would be like a vacuum source over here. It sucks in air on this side and draws it around and keeps that spinning there. So this is a typical layout for a vacuum system. You've got air going to these instruments, each one of those instruments, and it's getting basically drawn to this vacuum pump right here and then blown overboard. The reason they do that is because if you could say, all right, well, why don't we just blow air into all these systems? Why do we have to suck it out? The problem is these vacuum pumps, they can fail. And when they do fail, parts and stuff like that will go through the system and get caught in these instruments and they basically destroy them. So what they do is they just have a filter, which is very simple. And it's just, this leads to outside air. But it would suck in the air. The air would go through this, so it would be free of impurities. Then it gets drawn through the instruments and across those vanes, driving those, instruments, whatever it may be. So again, and then also a couple extra gauges. You're going to see a suction gauge on the aircraft. It's just to tell you how good your vacuum is. Usually between 4.6 and 5 point something is a decent vacuum for most aircraft. It weakens as you get higher. If you go to a real high altitude, the vacuum system may not be strong enough to provide enough power to keep those gyroscopes spinning. But you'd have to be at a pretty high altitude there. Remember I showed you that Venturi? You guys remember this? That's what this is for. It's to create a vacuum. So instead of actually having a vacuum pump like here, this just mounts on the side of the plane, like you have it mounted. If the plane was moving forward like this, it'd be mounted on the side like this, on the front. And it just creates a vacuum, enough of a vacuum that you don't need a vacuum pump here. The drawback to these type of systems, and you see them a lot of older aircraft, like 40s, 50s vintage aircraft. The problem with them is they don't work when the plane is just sitting on the ground. The plane has to be moving through the air. So it's not this. You're not going to fly a plane in IFR conditions that has just this. It has to have vertical, or it has to have a vacuum. All right. Turn coordinator, turn slip. I think the last thing we have to talk about is time. Yeah, we've gone through that. I'm not going to dive into that here. Let's see here. And one last thing I think we have to talk about is the compass thing. Yeah, okay. So they go into they talk about this flux gate compass. It's not something you'll see on the test initially. They are used in some of the newer avionics, but essentially what a flux gate compass is, it's just another way of determining what your heading is without some of the conditions some of the problems that we have with a magnetic compass. So magnetic compass, this stuff is important. So this is always going to point to magnetic north, right? And we all know how compasses work. It'd be the same as if we held a compass in our hand, we're flying up there. But the problem with compasses is that they're wobbling. They also have other types of errors that you may not know of. So they have, there's acceleration errors and magnetic dip errors and things like that. So let's see if they've got here. Okay. So on the Earth, in this diagram, you're not going to see this in the books, but there is what's called the true North Pole, and then there's also the magnetic North Pole. I don't know if you guys know this, but the magnetic North Pole is constantly moving, as much as like 40 miles every year. It's shifting around, and that's because there is, the Earth's core is shifting and stuff like that. So one day you may be at, 1 second, you may be at 90 degrees. You may be, stand outside your house and point to a specific point. Let's say I'm looking at another house, and it's saying, okay, well, that house is in the direction of, 360 degrees or something like that. The next day, or maybe a month or two later, you do the same thing, and it's going to say it's at, use your compass, it's going to say it's now at, 359 degrees or something like that. So that would take over time, but it could affect the compass reading over time like that. Yeah, you had a question. Yeah, Trey.
If I remember correctly, the current magnetic North Pole is somewhere like in Greenland, or like it's not in the North.
It's south. It's well south of the North Pole, and I'm not sure. I think they've got a diagram of where it's at. So
It's constantly
it is.
It doesn't.
What's that now?
Well, the Earth never is moving. It's not moving just like this. It's kind of like a not perfect circular.
Yes, and it tilts. So if you look at here's the tilt right here of the true north or the poles. These are the poles that the Earth rotates around, the true North Pole and true South Pole. So as the Earth rotates, it's rotating like this. There's our true North Pole and our true South Pole. The magnetic poles, however, are different. I mean, they're they're going to show up here. And then we get it back. They show it here, but it's like I thought it was someplace in Canada, northern Canada, where the true north or the magnetic North Pole is.
Yeah.
What's
I remember correctly. It's like the top.
yeah. Mm-hmm. And because of that, you have these variances in the magnetic poles, and it's dramatic. It's your true north in like Washington State, for instance, could be off by as much as 20 degrees from magnetic north. And so those are some of the things that we have to deal with there. And I tell you what, let's pick this up next week. If you guys have a chance, read through this. We're just going to touch on this a little bit next week. It is important. I'll explain to you the different types of errors that you can account for, or that you can expect in a compass. But there are acceleration errors when you're on an east or west heading. If the aircraft is accelerating, it's going to show it different areas of distance. Oh, that's right. Yes. We'll actually be meeting in 2 weeks. So we're not going to have our class next weekend. Yep. Now, if you guys want to, I can meet you over at the Bearwood Airport. I can have the sim set up there if you've got time. I'd be happy to go over there and meet with whoever wants to fly the sims there. So that's a possibility. What's that? Next Saturday, I would be at the Bearwood Airport is where we'll be at. Okay. It'd be the same time, 9 to 11. All right, perfect. And if you guys have any questions, as always, you can get a hold of me. You